Class, welcome back to CSC 143. We're in week 9 looking at binary trees, and today we're going to be looking at binary search trees. To give you an overview of where we're at, here's the rest of our course so far, and here is we're looking at binary search trees. There's also a section of the book on search trees that are parameterized, which is the same kind of stuff that we covered in 17.1, but it allows you to use any data structure. And I'm not actually going to go over that because that's not something that I have my students do, but you can take a look at it in the book. And just to remind you, 143 is the second of 2 Intro to CS programming classes we offer at South Seattle College. And this is information on where you can get that book available online. So far we've been talking about general binary trees with no restrictions on them, and actually regular binary tree is not all that useful. We've been learning algorithms because you can apply these algorithms to any type of binary tree, but really the binary trees are only super useful if they're search trees. And the restrictions on a search tree is that you have, for any given node, all the values less than it go on the left child and all the values right of it go on the right child. Once you do that, you can now search very quickly, just like we were able to do in binary searches in arrays. But we're no longer restricted to having a flat array of data, and that allows us to be able to add and move data around quicker. Amelia did note here that the data is divided so that half are in the left and half are in the right. That's the ideal. That's what we call a balanced binary tree. That's not always the case, and we'll discuss later that you can have degenerate cases that don't look like a binary tree at all. But as long as this is true, the data is less than on the left and greater than on the right, then it's going to be a binary search tree. There's an edge case. Well, what if you have duplicate values, which you are allowed to have in binary search trees? You just have to pick consistently whether they're going to be on the left or the right. So here she's drawn them on the left. So to construct a search tree, I want to make a major distinction that's not obvious from the book or from the video so far. All the stuff that we've been looking at so far, we have not had to actually do a lot of code, with any code, for adding nodes other than just creating a node. If you actually have to go in and add nodes, you need to do a different kind of code that we call x equals change x. So here you can see this code where we assign the left or the right to be the recursive call. So this is a paradigm we call x equals change x. It's a very difficult concept for many students to understand. So I want to point out that when do you need this x equals change x? Because so far we haven't had to use that in the code. You need this when you're actually going to change what's in the tree. Let me just jump ahead for a second. So here, imagine that we've got this tree and we want to add a node in. That's where you're going to have to do the x equals change x. So let's go back. So this code is only going to have a constructor to generate an empty tree, and the only thing that you're going to be able to do to add to it is call this add method. So why is that? Because previously we had a method where we could construct a node and give it any left and any right. Well, now a binary search tree has this added constraint that things on the left have to be less than it and things on the right have to be greater than it. So we must enforce that through this method here. If we just allowed users to create a node with any arbitrary left and right, that would break down. So this forces that constraint. So that's an important part of this. So let's take a look at this code. So the search tree is just like the binary tree we've looked at before. The only thing it contains for its memory variable is going to have the overall root. Then to construct it, you just simply create a null root. Then to add a node, you just take a value and it calls the add method with that value. So the real work happens here in the add. Really, nothing's happened here so far, right? So when we add something, if the root's null, so it's empty, then we're going to create a new node and then we're going to return that root here. And again, this is part of that x equals change x. Because this entry node returns the new node, you can now say x equals change x. Otherwise, we check whether the value is going to be on the left or the right hand side, and we add it there. So let's go back to this code example here. So in this tree here, we want to add 5. So it's going to come to the first node here, the root's not null, so it doesn't do that. Instead, it's going to say, well, is it on the left-hand side or the right-hand side of 3? And 5 is on the right-hand side. So we recurse with this node here. And then we say, is it on the left-hand side or the right-hand side? So it's left. So we can now add it to the left. So it gets a little confusing here because we're about to recurse now using the left of this node here at 9, but there's nothing there. So that's the confusing part. But what is there is a null, right? That's what the root.left has. Every node has a left and a right, even if they're null. So we're going to call it with null. This is where this code comes in here, even though we didn't need it up here. Now this root is null, so it's going to create a new node with the value 5 and return that. Now we're coming back here, and we're going to do that x equals change x to set the left node of this 9 to be that 5. So that's where the real change ends, but the code isn't over yet. And actually, this isn't super critical, but note that on its way back up the return chain, it keeps on setting these nodes. It's actually going to reset the left here, or sorry, the right, to be this node again, even though it didn't change. And if we had to keep on doing that, it would keep on setting things all the way back up the tree. Finally, we get up to the very top, which in this case is just this node here, and we return the root, the original root. That it hasn't been changed, but it could have changed. So anyways, this is the x equals change x paradigm. A common problem in our exams, but something that is not represented in practice because it's just impossible to do in a computer, is to have students take a list of items that they want to put into a binary search tree and then draw the binary search tree. So let's go through that. Here I've got a list of names from a popular cartoon. We're going to write them out into a binary search tree. Now I want you to notice that the order in which the names are presented to us makes a difference in what the binary search tree will look like. So I have to follow this order exactly. We're going to start with Lisa. So Lisa. Then I'm going to take Bart. Now is Bart less than or greater than Lisa? It's less than. So we go over here to put Bart. And then Marge. Is Marge greater than or less than Lisa? It's greater than. So far, so good. It's going to get a little bit more complicated. Now we come to Homer. So is Homer less than or greater than? It's less than. Is Homer less than or greater than Bart? It's greater than. So this is where it ends up. Maggie. So that's greater than, but it's not greater than Marge. So Maggie goes here. Smithers is greater than Lisa, greater than Marge. So Smithers goes there. Flanders. Flanders is less than Lisa, greater than Bart, less than Homer. And then Krusty, less than Lisa, greater than Bart, greater than Homer. So Krusty goes here. And then the last one is Milhouse. It's greater than Lisa, greater than Marge, but it's less than Smithers. So this goes here, Milhouse. Now, there's an important safe double check that you can do. If you do an in-order traversal of these, remember in order is when we come to the underside of an item. And remember that for Bart here, so we're going to skip Lisa. When we come to Bart, it may not appear at first, but actually we can get to the underside of Bart here. We're not blocked by this branch going off to the right. So Bart is actually the first one. Then we come down, we can't get it to the underside of Homer. We can get to Flanders, so that becomes 2. Homer is 3, Krusty is 4. We come back up here. Lisa is 5. Can't get to Marge yet, but we can get to Maggie, so that's 6, 7. And then we can't get underneath Smithers, 8, 9. And then we're done. Now, did you notice anything about the order of these numbers? B, F, H, K, L, M-A-R, M-A, that's Maggie, M-A-G, then M-A-R, then M-I-L, and then S. these are in alphabetical order. So when you create a binary search tree, if you then perform the in-order traversal, you can determine whether you did it right or not. And that's a very important characteristic that makes it easy. So that is how we do it with names. Let's try another one with numbers. So the first number here is going to be 3. You should try to do the rest of this on your own. Stop the video, try to do it, and then come back and see if you did it right. So the next one after 3 is 5, so that's greater than. 2 is going to be less than. Then 1 comes down here. Having a little trouble with my pad. Okay, 4 is greater than 3, less than 5. And then 6 will come down here. So hopefully if that's what you got, the in-order traversal will make us come down here. This will be number 1. Then this will be number 2. This will be number 3. We'll come down here. This will be number 4. This will be number 5. Finally, number 6. So that is correct. So as I mentioned, the great thing about binary search trees, and the reason why pretty much the only trees we use are binary search trees, is because they allow very quick searching. So it's very similar to the binary search we did for arrays. If you recall, for arrays, within an array oriented left to right, we split the array in half, and then we determine is it less than or greater than. If it's less than, we take the left half and we search there, and if it's greater than, we take the right half, and we just keep on recursing like that. So it's very similar. First of all, we have a helper function, as we need to do with all these tree functions, just to grab the overall root. Then similar to our arrays, in the arrays we had a case of failure when the min and the max switched places. The equivalent here is that if the root is equal to null, there's nothing left to search, so we're going to return false. In the array, if we found the value, that would be true, and we would return that index. So here we check to see whether we found the value. There isn't an index to return here, so we simply return true, that it does exist. That's a little bit of a limitation in a binary search tree. And then the last recursive cases are either it's in the left-hand side or it's on the right-hand side, and we recurse. So it's very similar to the way that we would do searching in an array. The next topic to discuss is binary tree complexity and order of algorithms. So I'm going to read these, go over these slides, but I'm going to jump back in just a second to show you an example. So the interesting point about a binary tree is that at each level, the number of nodes doubles. So if you have a level, you express it as k, you can have 2 to the k values in that level. And that implies some interesting functions about how deep a tree needs to be and how long it takes to look in a tree. And so let's take a look at an example here for what this really looks like. Now this is a very trivial tree example, but it just graphically shows us and reminds us that at every level you have twice as many choices. So it goes from 1 to 2 to 4 to 8 to 16, etc. And it's because of that splitting at each level that we can say that for n nodes, you can construct a tree of size log n in ideal circumstances and be able to fit those nodes in. And to be able to find any given node, you can do that in log n, log base 2 of n, because you're splitting the tree in half at each point, so you should be able to find it within log base 2 of n decisions. And again, remember that complexity, the constants don't matter, so this isn't an exact formula, but it's good enough for the order analysis. Now I mentioned earlier that the order in which the items are presented to you and added to the tree makes a big difference in how the tree looks. In the worst case, if you're given the items in sorted order, you're going to end up with the tree looking like this. It just keeps on going off to the right forever. That is the worst possible case, because then instead of being able to search your tree in log n time, cutting the items in half each time, you're actually going to take order n time. So in order to avoid that, there's something called a balanced binary tree, which we're not going to talk about or at least not really learn about in this book, but just know that there are algorithms so that when you insert a binary tree, it automatically rebalances the tree, which, as you might imagine, involves a lot of work, but that's important to keep binary trees balanced so that those algorithms work as efficiently as they can. And that is the end of this topic. So we won't be covering parameterized tree implementations, but it is a really great thing to look at in the book. There are lots of examples in Practice It that you can go through to do all of these functions, so please go take a look at those in the Practice It website, and I have videos for many of them. So if you've liked these videos and find them useful, please like and subscribe. That helps other people find my series. Thank you very much.